All right, folks. So now we got delta G, the last of the three thermodynamic values. Delta G is called Gibbs free energy, named after a physical scientist or physicist, Gibbs. Gibbs free energy takes into account both enthalpy and entropy and temperature, because entropy is temperature dependent. So if you want to know whether or not a reaction is spontaneous or not, the Gibbs free energy is going to tell you that. Now, we do have a formula that if you know the enthalpy and you know the entropy, you can get the Gibbs free energy and determine the spontaneity. But at first, oh, and it's right here. Okay, we'll talk about that in a second. But at first, let's just define Gibbs free energy. Okay, if you have a Gibbs free energy, change in Gibbs free energy that is less than zero, that's a spontaneous reaction. If you have a Gibbs free energy that's greater than zero, then that is a non-spontaneous reaction. That's a reaction that would require some additional help, right, to make it happen. That's a reaction that's not going to want to happen on its own, okay? And if you have a Gibbs free energy that's equal to zero, we say that reaction is at equilibrium. Now, for you biologists, I remember taking freshman bio and them showing some figure of the life cycle of a cell, right? So like, oh, I don't even remember what that crap is called, right? But there was a part in that life cycle of the cell where it was like delta G equals zero, cell death. This is the Gibbs free energy thing that they were talking about in your freshman bio class, if you remember. Some bio teachers just go right over that, right? Because they don't even remember doing it, right? Which is okay. If you calculate delta G for a reaction and you find that it has a positive delta G, all that means is that the reverse reaction is actually spontaneous. So if reaction is non-spontaneous in this direction, it would be spontaneous in the reverse direction. Just want to draw your attention to that. Okay, here is the most important equation of the entire night. You got to write this down and you got to memorize this for Thursday, August 8th, man, the last day of the class. Woo! That is a week from Thursday. Y'all are going to be done. This time, a week from Thursday, you guys in Harrisburg, you'll be done. And y'all in Lancaster, you're going to be on your way to being done. That's crazy. Anyway, this formula you got to memorize. This is such an important formula. There's not many formulas, okay, again, after exam one. Remember, we had that formula sheet on exam one because there was so much. Oh, my goodness. Okay, but this one you just got to memorize. And here is the formula. Here's the relationship between enthalpy, entropy, and spontaneity or Gibbs free energy. This formula says the spontaneity of a reaction, the Gibbs free energy, is equal to the enthalpy minus the temperature in Kelvin times the change in entropy. Now, this is where I was saying you got to watch out for the units, man. Okay, this guy's in kilojoules. So I would divide remember the S value is in joules. So I would divide that number by 1,000 before you plug it into that equation. Okay, so the change in free energy, the spontaneity reaction, is equal to the enthalpy minus the temperature times the entropy. Yeah. Cool. This is going to give us four scenarios. And so that equation is the most important equation of this chapter. And if I had to pick a most important slide of this chapter, I'd pick this slide right here. If you stop and think about it, there are four possibilities for a reaction when it comes to spontaneity. You can have a reaction that has a negative delta H, so is exothermic, and is becoming more random. This is as good as it gets if you are rooting for spontaneity. That is a reaction that will always be spontaneous. If you have an exothermic reaction, negative delta H, and you have a reaction who's increasing its entropy, positive delta S, then it's always spontaneous, always spontaneous. Okay, let's talk about the opposite. This is like the coffin nail when it comes to spontaneity. If you have an endothermic reaction where the products are less, what's the word I'm looking for, stable than the reactants, you got an endothermic reaction and the system's becoming more ordered, that is, that reaction can never be spontaneous by itself. Never, ever be spontaneous. Okay, because if you think about it, positive minus a negative is positive. That delta G is always going to be positive. If you think about this one, that's always spontaneous, a negative minus a positive, that's always going to give you a negative number. That's why it works out that way. The other two scenarios require you to know the temperature. They are the temperature dependent spontaneity scenarios. So let's look at the first one. What if we have an exothermic reaction, which is good if you're rooting for spontaneity, and a reaction that's becoming more ordered, which is bad if you're rooting for spontaneity? Well, if you want your answer to be negative and delta H is negative, then we want this to be smaller than that. So at low temps, in reactions with a negative delta H and a negative delta S, they will be spontaneous only at low temps, because at low temps, this temperature times delta S will be less than delta H, and you get a negative number. Now, the opposite is true. A endothermic reaction that is becoming more random. So this is like the ice melting, the water evaporating, the table salt dissolving, right? Those events that are endothermic but becoming more random, they are only going to be spontaneous, occur on their own at high temperatures. So think about it. Ice doesn't melt until you hit 0 degrees Celsius. It's temperature dependent, right? Okay. Think about like evaporation rates. Okay. The hotter it gets, the more the water tends to evaporate, right? Okay. Now, technically, water will slowly evaporate at any temperature above 0 degrees Celsius. Okay, but it's much faster at higher temps. So, you know, what you're looking for here, if you're rooting for spontaneity, since it's endothermic, that's bad. You want the entropy component, which is good, increasing entropy, to dominate. So you want temperature to be high, so that temperature times that entropy is greater than the delta H. So confusing, but before you walk into that third exam on the 8th of August, make sure you got this slide down, Pat. Super duper 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 important. Here's that whole slide in a table. Who doesn't like a good organized table? Right? That's a good organized table. It's everything I just said, right? Picture's worth 1,000 words, okay? And here that might be true. I probably did 1,000 words there or something, right? Again, look at the top one. Exothermic increase in entropy, can't stop it, baby. Okay? Endothermic decrease in entropy, can't get it to go on its own. And then the other two are temperature dependent. Exothermic decrease in entropy only at low temps, and then endothermic increase in entropy only at high temps. Gotta know that. Gotta know that. Gotta know it. You do not have to use the delta G equals delta H minus T times delta S formula to predict spontaneity. If you have a list of standard Gibbs free energy values, that's right. If you remember that table that I just showed you in the book, it had 3 columns. First column was delta H, middle column was delta G, last column was delta S. So you can predict the spontaneity of a reaction just using that middle column if you have the values. If not, you'll need the delta H and the delta S, which I actually prefer. We'll explain why. You can do more with that than this. But same formula. I told you that formula is going to get repackaged 2 more times. Here's the last time it's getting repackaged. The change in spontaneity or Gibbs free energy of a reaction under standard conditions is equal to the sum of the standard Gibbs free energy values of the products times their coefficients minus the sum of the standard Gibbs free energy reactants times their coefficients. So I would like you to try this problem. Go ahead. Tell me, is this combustion reaction of ethanol spontaneous or non-spontaneous? Go ahead. I got a negative 2,862.6, and that is kilojoules per mole, folks. Negative 2,862.6 kilojoules per mole. Okay, so again, it's 4 times the CO2 plus 6 times the H2O liquid minus 2 times the ethanol plus 6 times 0. And yeah, people have a hard time understanding, well, hey, if you have a non-spontaneous reaction, all hope must be lost, right? This reaction can't happen, right? Maybe it's positive delta H and negative delta S, and you say, well, this reaction would be non-spontaneous all the time. I can never get it to go. That's not true. What that means is that the reaction is non-spontaneous on its own. But if we couple it with a spontaneous reaction, if we put energy in from the outside, right, then we can get the reaction to happen. So it's not like all hope is lost. Now, you guys aren't taking the final because it's the summer, but boy, does the American Chemical Society, because we give the ACS final, boy, do they love to ask a question like this. And they'll be like, uh, which of the following sets of conditions could make this non-spontaneous reaction occur? Right? And they love to, for some reason, say, like, add a catalyst, right? Catalysts can't make a non-spontaneous reaction spontaneous. All that a catalyst can do is take a spontaneous reaction that would happen on its own anyway and make it more spontaneous, right? So a catalyst cannot suddenly take a reaction that would not happen on its own and make it happen now. The reaction has to be able to happen on its own in order to find something to speed it up. Okay, so watch out for that. I mean, I want to talk about entropy in a little bit more detail. I'm going to talk about entropy and a phenomena called molecular complexity. Here's where this gets at. The more complex the Lewis structure of a molecule, the greater the entropy in that molecule. I know what you're thinking. What? Okay, but it's true. Here's what's going on. If we look at, for example, argon, okay, which is an individual atom, and we look at its entropy value, it has an entropy value of 154.8. But if we look at NO, okay, nitrous oxide, it's got a higher entropy. It's more random at 210.8. What's going on here? Molecules are always more complex and have a greater amount of randomness than individual atoms. I'll show you what I mean. Think about this. Here's an atom of argon, and we'll do a molecule of NO, okay, whatever, okay? So we're not going to finish the Lewis structures, but let's just imagine this. It doesn't have to even be NO, right? It could be any two atoms bound to each other. If you have a bond, you have a lot of randomness that you can exert. Here's what I mean, okay? If I have a bond between X and Y, what could happen here is this bond could elongate, like Y could move away from X, it could stretch, X could move away from Y. The bond could bend, right? So maybe it could bend a little bit, right? So it could, Y could move down here, Y could move up here. If it's a single bond, the bond can rotate. So Y could spin around, right? They could spin together, they could spin counterclockwise. Okay, there's a lot of randomness when you start putting atoms together. And the more bonds and the more atoms you start creating, the more randomness you're going to have. Now, if you're an individual atom, there's nothing else for you to move relative to. Your electron cloud can distort. So the bigger your electron cloud, the greater the chances of, electrons randomly going over here and the side getting a little smaller and the side getting a little bigger, right? So bigger atoms have a higher entropy than smaller atoms. But molecules almost always have a higher entropy than individual atoms, unless that atom would be huge and that molecule would be tiny. Okay, let's look at some other examples. So take a look here. Now here we have two molecules, carbon monoxide and ethylene. Okay, and we're going to try to figure out why does ethylene, even though they have the same molar mass pretty much, why does ethylene have a greater randomness or entropy than carbon monoxide? Well, glad you asked. If we draw it out, ethylene just has way more bonds. And a lot of those bonds are single bonds, which is what's going to allow this molecule to do more distortions. So if we draw carbon monoxide is a triple bond between carbon and oxygen. And there's not a whole lot these two atoms can do. Because they're triple bound to one another, this bond can't really rotate, right? It's kind of locked. Like maybe it can do a little bit of this, right? But it can't spin, okay? All the bond can really do is stretch a little bit, right? They could move together. They can move together this way. They could go in opposite directions. It can't really bend too much because it's a triple bond. It's super strong, super rigid. Okay, but if we draw ethylene, C2H4, Oh my goodness. This molecule has a lot of different distortions it can do. First of all, these C to H bonds are all single bonds. So those bonds can rotate. Okay, like the hydrogens could spin around. Okay, and now since he said they could, these two hydrogens could do one of these, right? They could move together. Okay, these hydrogens that are perpendicular or diagonal from one another, they could move, right apart. Now, this central carbon-to-carbon bond is a double bond, so it can't rotate. But there's so much more randomness here in these molecules. Okay, these are called stretching frequencies. And then if you take organic chemistry, you'll learn a laboratory technique called infrared spectroscopy, where if you hit molecules with infrared light, you can cause them to wiggle and jiggle and stretch. You can cause these molecules to wiggle, jiggle, stretch, and have different vibrational frequencies. There's another instrument called Raman spectroscopy, similar to infrared light, makes molecules wiggle and jiggle, and you can pick up on these stretching frequencies, see what kind of bonds you have in molecules. So molecular complexity, folks, the more complex a molecule, the more random it is because there's more stuff that can bend and twist and wiggle and jiggle and vibrate and move all around. So molecular complexity and entropy. I would like you to predict. I took this from an old textbook, full disclaimer, don't sue me. Okay, I would like you to predict, I would like you to go down through here, and I'd like you to predict which one has the higher entropy. So can you look at these? Sometimes the states of matter matter, sometimes you just have to look at the size, right? I want you to take a solid 2 minutes, okay, or so, okay? I'll look at, there was a 651. And I want you to go down through and circle or write down the one that you think would have the higher entropy, essentially the greater molecular complexity. Go ahead. All right. So here we go. Hopefully, here in this first one, you picked carbon dioxide. Why? It's more complex, right? This is 2 atoms. That's 3 atoms. 3 atoms have way more things they can do, right? All three, the two ends can move together, they can move apart, they can move, they can, they can do all kinds of stuff, right? Okay, that's way more complex than just 2 atoms. Here, hopefully you picked methanol in the gas phase, right? The gas phase is always more random than the liquid phase because the molecules are flying around like crazy, right? They're not, have no intermolecular forces. They're not locked in. They're on their own. And C, hopefully you pick CO2 because that's a molecule versus an atom. D is a tough one. These are both tetrahedral. Carbon in the middle, 4 hydrogens coming off of it. Silicon in the middle, 4 hydrogens coming off of it. The answer is silicon tetrahydride. And that's just because silicon's a bigger atom. So it's a tie in their molecular geometry, their shape. So it's going to come down to number of electrons. Silicon's got more electrons flying around. So it's going to be bigger. Hopefully you pick propane over nitrogen dioxide. Okay, propane, look at all those bonds. Oh my goodness. We got 8 C to H single bonds. We got 2 C to C single bonds, as opposed to here where we just have 2 N to O bonds. Way more complexity here. Hopefully you pick the aqueous phase for sodium bromide. Okay, that's way more random than the solid phase. And hopefully you pick PCl5. I should have put something on the right. The answers were all on the right. If you picked everything on the right, you got it right, okay? It's like the kid that fills in C for everything, right? Okay, this would be that kid's lucky day. PCl5 is a trigonal bipyramid molecular geometry as opposed to a trigonal pyramid. And the 2 extra P to Cl bonds, so you got 2 extra phosphorus chlorine bonds, that creates more randomness. Yep. So I love to ask me a good question on molecular complexity on the test, the third test, not the second one. So watch out for that, folks.